In the Bohr model of the atom, an electron is visualized as orbiting the nucleus. Now, this isn't what actually happens in an atom, but it's a way to visualize the different energies the electron can have. Since energy is quantized, there's only a certain discrete number of orbitals, meaning that an electron can only have certain values for its energy. All the energy levels that the electron has in the atom are going to be negative energies. So in electrostatics, when a negative charge and a positive charge are attracted to each other, we say that they're electrostatically bound, so they have negative potential energy. Now, the electron does have kinetic energy, but it's not enough to overcome the negative potential energy it has, trapping it in the atom. The further out the electron gets from the nucleus, the less bound it is. So going further and further out into the nucleus or to higher orbitals means the electron has higher energy. In order for an electron to go from a low orbital with low energy to a higher orbital with higher energy, it needs to gain energy to do that. And the way it gains energy is by absorbing a photon or a light particle. On the other hand, if an electron in a high orbit with high energy drops down closer to the nucleus to a low orbital with less energy, it has to release energy. That energy is also released in the form of a photon, which is emitted. Now, because there's only certain energy levels or orbitals that an electron can have in a given atom, each orbital is assigned a quantum number n, which represent the different energy levels that an electron can have. Because there's only certain values of this energy level, n has to be an integer. The first quantum level, n equals 1, corresponds to the ground state. This is when the electron is closest to the nucleus and therefore is most electrostatically bound to the nucleus. This involves the least amount of energy in the system, and this is also the state at which the electron is most stable. Any quantum state above n equals 1 means that the electron has gained energy from the ground state. These states are called the excited states. If an electron absorbs a photon with very high energy, it can ionize, which means it gains enough energy to overcome its negative potential energy binding it to the nucleus and escape the atom. When light is emitted from a very hot gas, the result is an emission spectrum with only very particular wavelengths of light coming from the gas. This is because the gas has high energy electrons, which are trying to return to lower orbitals, which are more stable. When they do that, they emit photons. Because there's only certain energy levels within the atoms of that element, only specific photons are emitted. A cold gas is going to tend to have low energy electrons. If photons are shot through that gas, since its energy levels are discrete, will absorb photons, but only photons that correspond to very specific energies. And as a result, if you look at the light after going through the gas, there'll be very specific wavelengths of light that are missing. Emission and absorption spectrums arise from the fact that an atom can only absorb or emit photons of discrete energy levels. So for this hypothetical atom here, with 3 possible states, the possible transitions are, it can go between state 1 and state 2, which has an energy difference of 5 electron volts. It can go between state 2 and state 3, difference of 4. It can go between 1 and 3, which has a difference of 9 electron volts. That means that this atom can absorb or emit a photon with 4 electron volts. It can absorb or emit one with 5, or one with 9. Now, let's say, for example, there's a photon with an energy of 6 electron volts. This photon won't be absorbed or emitted by the atom. If there happens to be a photon with an energy greater than 10 electron volts, that photon is able to ionize the electron and have it escape the nucleus entirely. This is an example question that gives energy levels for a hypothetical atom. And it says in this atom, an electron goes from n equals 2 to n equals 4. And it asks to calculate the wavelength of the photon either absorbed or emitted in the process. So when it goes from 2 to 4, the electron is gaining energy. So in order to do that, it has to absorb that energy in the form of a photon. Now to calculate the wavelength of the photon, I'm going to use the fact that the energy of a photon is equal to Planck's constant times frequency. And since speed of light equals frequency times wavelength, this can be written as energy of the photon is Planck's constant times c over wavelength. Solving this for wavelength yields Planck's constant times speed of light over the change in energy, which in this case would be the energy of the photon absorbed. And then the plugging in numbers here involves a lot of calculation. So that's Planck's constant times the speed of light. And then the gain in energy here is 4 electron volts. But in this equation, I'm going to use joules. So I'm going to convert electron volts to joules by multiplying by 1.6 times 10 to the negative 19. And this is going to give a final wavelength of 3.1 times 10 to the negative 7 meters, or 310 nanometers. The second example shows 6 possible transitions for an electron energy level within an atom, and it's asking which of the transitions given corresponds to an emission of a photon of the greatest wavelength. So the first thing to look at here is that a photon is being emitted. And since a photon is being given off, that means that energy has to be going down, which means that it's looking at either C, D, or E, because those all look at going from a higher orbit to a lower orbit. And since energy is going down, that means that frequency has to go down as well. And then because the speed of the photon is constant, if the frequency goes down, the wavelength goes up. So what I'm looking for here is the smallest change in energy, which means the smallest change in frequency, and the largest change in wavelength. And in this case, that's going to be transition C.